Okay. From the book I'm referring to, this is section 10.1. It's on sequences and summation notation. Doesn't that have a nice little ring to it? Summation notation. This is a long section, so we're only going to do part of it today, okay? So we'll only talk about the sequences part, okay? Definition of sequence is a list of numbers separated by commas. Okay, so it's just a list of numbers. Infinite sequence and let me know if I'm going too fast, guys. Is a sequence that never stops. So let me give you an example of an infinite sequence. It's called the Fibonacci sequence. Okay, so a finite sequence. Is a sequence that stops. Okay, let me give you guys a finite sequence. 3, 6, 9, 12, 15. Okay, couple things about a sequence, okay? Every sequence has a number called n. N is the term number. So for the first term, n equals 1. Second term, n equals 2. Then n equals 3. Then n equals 4. Then n equals 5. Now, stop there. Does that make sense? So every sequence has a term number, okay? Every sequence has a sub n, which stands for the answer. Now, doesn't that make sense? A-N, answer, A-N. Answer in that position. So the answer in the first position is called A sub 1. That's the first answer. The answer in the second position is called A sub 2. The answer in the third position is called A sub 3. A sub 4. And then A sub 5. For the finite? No, it works for infinite also. Okay? All right, so you have term number, answer in that position. Term number, answer in that position, term number, answer, term number, answer, term number, answer, okay? Because you have those, what we can actually do is we can graph a sequence. And the ordered pairs are going to be term number and then answer in that position. Term number, then answer in that position. Okay? Now, anybody think they can get some ordered pairs for this finite sequence? Okay? There should be about 5 of them. Anybody know the 5 ordered pairs? And hang on. Okay. On the 2 axes, this axis is labeled N for term number. This axis is labeled A sub N for answer in that position. You guys see that we have to go up to 15, right? So on the A sub N axis, I'm going to go like this. 2, 4, 6, 8, 10, 12, 14, 16, just so I can get all the numbers on there. On the term number axis, we only go up to 5. So let's go 1, 2, 3, 4, and 5. Sequences can graph as any kind of shape that you've studied. What is the name of this shape that you guys studied? Just say it, guys. Linear. So this is linear. Will a sequence always graph as linear? No, it won't. It could graph as quadratic, a half of a parabola. It could graph as a cubic, okay? So it could graph as just about anything. Now, do you remember from Algebra 2? You guys talked about domain and range. Now let's think about domain. Domain is like your x-axis. So we use 1, 2, 3, 4, 5. First term, second term, third term, fourth term, fifth term. Okay? Is there the half term in a sequence? Is there the 1.2 term in a sequence? Is there the 3.5 term in a sequence? What do you guys say? Yes or no? No. Okay, so this has to be, you can't have any fractions, you can't have any decimals. So what do you guys want to call those? Raise, please. So numbers that are not fractions nor decimals. Real numbers are fractions and decimals. Integers, okay? So integers. And you think you could have the negative first term? So no. Okay, so, all right, so integers greater than or equal to, what's the first term number? Term number 1. Good. Integers greater than or equal to 1. The answers in these positions can be fractions and decimals. So what did you guys call that? Real numbers, yeah. Okay. Okay, now, 2 things you can talk about a sequence. You can talk about a pattern, and you can talk about a rule. Pattern represents what you do to the previous term to get the next term. What you do to the previous term to get the next term. So it has nothing to do with the term number. It just, what's the relationship between 3 and 6, 6 and 9, 9 and 12, 12 and 15. Anybody see the pattern? What are we doing every time, Autumn? Add 3. That's the pattern. Very different than the rule. The rule is what you do to the term number to get the answer in that position. So what you do to the term number to get the answer in that position. So the question is, what do you do to 1 to get 3? What do you do to 2 to get 6? What do you do to 3 to get 9? What do you do to 4 to get 12? What do you do to 5 to get 15? And the rule is always much more important than the pattern. So anybody know what the rule is? What do we do to the term number to get the answer in that position? Autumn? Yeah. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. So the rule is 3 times the term number. So 3 times n. Now, once you know the explicit rule, you can find any term of the sequence. So I could ask you the 100th term, and you would be able to, and you wouldn't have to generate 100 terms. You'd be able to use the rule to find it. So example 1. Write the first 4 terms of the sequence. Given the explicit rule. A sub n equals 3n plus 4. Second one, I'm going to have you guys see if you can generate yourself. A sub n equals -1 to the n over 3 to the n minus 1. And again, we want the first 4 terms. Now, I gave you a nifty one, didn't I? Okay, recursive rule. Gives any term of a sequence as long as the term before it is known. So in the recursive rule, you give the first term. And then the second part of the rule is what you do to that first term to get the next term. It looks like this. It looks like a sub n equals a sub n minus 1 plus blank. Now, normally, guys, you don't put anything in here for n minus 1. You don't put anything in there. All that means is look back 1 term. So it says after you get the first term, look back 1 term and add or subtract or multiply or divide it by something. The operation depends on what sequence you're looking at. Can we go back to our sequence at the beginning? 3, 6, 9, 12, 15. That was our sequence we started with. Okay? Now, could you write a recursive rule for this?